Okay, here we have a nice question which involves you using a little bit of a couple of equations, joining them together to find the final kinetic energy of an object. As usual, have a go and then press play. Okay, let's go for it then. So we're firstly told the mass of the object. That will be helpful for kinetic energy. We know the impulse, which might be a bit more, confusing for some students, and then we want to know the final kinetic energy. We also know that the object is initially at rest. You'll notice this coming up in a lot of questions, even in another question in this particular paper. It's always good to pay attention to that. That means we've got an initial kinetic energy of 0. So, how do we do this? First thing to do is think about our impulse. Our impulse tells us the change in the momentum of an object. So if you're told that the impulse is 2 Newton seconds, what you really are being told is its change in its momentum. Obviously, if momentum changes, we are also going to have a kinetic energy change. How do we calculate that? We're going to think firstly about our momentum. Well, we started off with 0 momentum because we were at rest. At delta P, we're going to get 2 kilogram meters per second. Now this is where students will forget that actually we have a couple of equations for our kinetic energy. Both are valid. Usually students would talk about a half mv squared, but there's another one here which you may not have used so much, which is p squared over 2m. So half mv squared and p squared over 2m are both ways into this. Why do we use this one? Well, we know the momentum is 2, we know the mass is 5, and so we're really just having to do 2 squared over 2 times 5, 4 over 10, giving us 0.4, which is why the answer here is A. Now obviously you could go and do this using the half mv squared formulation. However, you just find that actually it ends up being a little bit more involved and would take a little bit longer. Same answer though.